And this little picture is an example of how quickly the output of turbines scale up with size. These two circles, this one here is half the diameter of this one. And to calculate the area of a circle, I don't know if you remember back in your school days, pi r squared. So this circle is a quarter of the size of that one. So you get 4 times the output from a wind turbine that looks like that compared to that one. So the output from turbines increases quite quickly, much more quickly than any potential visual impact. So a bigger wind turbine tends to be more cost effective. You get more output from it. The energy in the wind, the power in the wind, is a much stronger dependence though than the area. You see the area, the amount of power increases quickly with size. The power increases even more quickly. It's a very steep curve. So this graph here, I'm trying to show wind speed in metres a second. 1 metre a second is 2.4 miles an hour. So most wind turbines are rated for output in something like a 30 mile an hour wind speed, because that doesn't occur very often in most places. But the interesting thing from this curve is that if you double the wind speed, there's actually 8 times the power available. So the wind speed is a very strong dependence, much more so than the area. And people are quite bad at understanding that. We usually feel that if the wind's twice as strong, there'll be twice as much energy there. But that's not true. There's much, much more energy there in stronger wind. And I imagine parts of your island are extremely good wind resource. I've just drawn a sort of random graph here, or carefully chosen random. This is a graph of wind speed changing with time, but with 3 different averages. So the blue line across here is an average with 2 metres a second. The red one is an average with 4 metres a second. And then there's another site with 8 metres a second average wind speed. And you look at that and say, well, it doesn't seem that much difference really in wind speed. But if you turn that into power available, which I've done on the next graph, you see how this one jumps up, the one with the better wind speed. That's because doubling the wind speed is 8 times the power available. And I think your site here would have something like 6.5 metres a second average wind speed. Something like that. So it's a pretty good site. 6.5 metres a second is what would be commercially viable as well. So we want to, in thinking about wind, we want to try and find a good site. And one way of doing that is to look at this. There's some data, a sort of computer model that the government produced called Noble. And it gives you average sort of computer model wind speeds based on square kilometres of area. And these are some figures from CAT, where I'm from, which incidentally is another disused slate quarry. So I've come from one slate quarry to another. And these are values from the computer estimation at 10 metres above the ground, 25 and 45. And these are some measurements we've actually made. So it only gives you a very rough indication of what the resource might be, because it's averaged over a map square kilometre. It's quite a big area, and it's only a prediction, it's only an estimate. But for your island here, at 10 metres above the ground, which is roughly the height you might be looking at with this sort of turbine, it says about 6.5 metres a second. And I think for here, that's probably going to be reasonably accurate, because most of it's straight over the sea, there's not much in the way on the whole. So that's the first thing you could do to get an indication of wind speed. If you were thinking of spending a lot more money in installing a much bigger scale wind turbine, you'd want to do really careful measurements of the resource to predict the output. So you'd put a tower up like this and leave it there ideally for at least a year and measure the wind speed at different heights and do lots of calculations. But it's probably not really worth it for such a small turbine on what we think is going to be a very good site. You'd spend a significant amount of the money that the turbine itself would cost just finding out that it was a good site. So I think it's probably not worth it, and particularly within the time scale as well. So this is a picture of lots of weird and wonderful wind turbine designs that people have tried. People have been making wind turbines for hundreds or thousands of years even. Electrical ones for hundreds of years though. They're often reinvented as well. There's nothing new under the sun, as they say. But this sort of turbine here is called a horizontal axis wind turbine. That's where it looks a bit like a propeller. Blades go round vertically. And they tend to be the most successful. They're the most successful, really. I can't really go into lots of these different ones, but that's the sort of thing you're looking at. I just want to explain to you a little bit about the output of a turbine in different wind speeds as well. This sort of graph is called a power curve. So along the bottom we've got wind speed, and vertically I'm plotting the amount of power per square metre of turbine size. So you can scale it up for whatever size turbine you might be interested in. So the power actually in the wind is that top blue line, and the next line, the red one here, is the theoretical maximum that you can get from any wind turbine. Because I said earlier, you're slowing down the wind with your rotor, you're extracting energy from it. If you try and be too greedy and slow the wind down too much, you just form an obstacle and the rest of the wind starts going round it. So there's a limit to how greedy you can be. That's called the Beck's limit, that's this line here. So you can't ever get more than that. But the turbine designs do reasonably well. You know, they get to sort of 80% or so of that theoretical maximum. So the most you could actually get is this sort of line here. And at the beginning, there's very little power available. Until you get to sort of 8 to 10 miles an hour wind speed, there's very little power available in the wind. So even if the turbine's spinning, it would just be going very slowly and not really generating much. It's once the wind starts going above that, you start getting some output. And then the output increases very dramatically with wind speed, as we talked about before. And then you get to about 30 mile an hour wind speed here. And at some point, you've got to say, my design's reached the limit of what it can cope with. And you've got to stop it generating any more or spinning faster, or it could be damaged. It doesn't happen very often. And you then need to decide what happens there. A lot of small wind turbines just rotate away from the wind to limit the output when the wind speed gets too strong. And this yellow line here is what happens to the output then. The output becomes quite low and then gradually recovers. And on a windy site like yours, you might spend more time in that sort of regime, losing some output. The type of turbines that are being suggested here have what's called pitch regulation. The blades, as they rotate, change angle a little bit to adjust the lift and the drag, the output. So you get this really nice flat line. You get the full output forever. It never really cuts out, even in a really strong wind. And because it's well controlled in a strong wind, it means you can have a slightly bigger area of blades relative to the generator, and it'll start generating at a lower wind speed as well. So you win at both ends because it's a little bit more sophisticated. Now, that power curve line I've just drawn you can combine with measurements of wind speed. So this red line here is an example of what a wind speed distribution looks like. So wind speed along the bottom, an amount of time that the wind blows at that speed. So you find often the wind is still, not for very much time. There's a maximum, a typical wind speed, and then the wind does blow at higher wind speeds, but not for very long. You virtually never get a hurricane. So that's the kind of distribution you tend to get. If you combine that line with the output of the turbine, you can work out the energy from each range of wind speed. So it's a combination of the power in the wind and how long the wind blew at that speed. And if you do that, you get a line that looks a bit like this green line. So the energy from the turbine comes from the higher wind speeds because there's more power there. But the downside to that is that the higher wind speeds don't occur so much. So you get a maximum that's shifted along towards higher wind speeds. And by doing that, you can then add up the total amount of energy from each wind speed and get a prediction of the total amount of energy that you'd expect to get from a given turbine on a given site.